Hello and welcome to another episode of EE361 Prelab Solutions. This is Professor Hirentrada, and in today's video, we are going to look at lab number 4. So let's bring up lab number 4 right here. Lab number 4 deals with op-amp circuits. Op-amp is short for operational amplifier, a very versatile chip in electrical engineering. There are many circuits that you can build with an op-amp, but the lab deals with the three most popular ones, which is the voltage follower, the non-inverting amplifier, and the inverting amplifier. So let's look at the background and the theory section. This is a typical equivalent circuit for an op-amp. So an op-amp is noted by a triangle with two inputs on the left and one output on the right. Each one of these inputs represents a input terminal which has infinite impedance between the terminals. So an op-amp has the property of having very high input impedance or resistance, if you will, and very low output impedance or output resistance. The two terminals on the left, one of them has a plus sign, the other one has a minus sign, and they note the non-inverting and the inverting terminal respectively. Now, when we say inverting and non-inverting, well, the non-inverting input basically appears exactly as it is in phase at the output, of course, with some amplification built into it. And the inverting input is actually going to take your input and invert it by 180 degrees. So the output of a inverting input is basically 180 degrees out of phase. And then op amps are usually operated in a feedback mode. Usually it's a negative feedback, meaning the output is fed back into the inverting input, and the negative feedback actually reduces the output. So it has the effect of reducing the output. So let's look at the questions in this pre-lab. Okay. Now, the background section has some background theory, and of course you would also learn this in E321 textbooks. But let's see. I want to do over two concepts. One is the concept of virtual short, which is mentioned right here. The other one is about the input current going into an op-amp. Okay, so when we apply, when we connect the output of an op-amp to its inverting terminal, we say it has negative feedback. And when you have negative feedback, we say that exists a virtual short between the two terminals at the input. Okay, that's because we say that the current and the voltage is equal to 0 at the input of an ideal op-amp. Okay, again, because it has infinite resistance between the two terminals, meaning there is no current flowing through the terminals, meaning I is 0, and I is 0, then so is V. Okay, so the voltage difference between the two terminals is 0, and the current is also 0. In reality, of course, there's a small amount that actually does go in. Now, the questions, basically there are three questions. The first one deals with the voltage follower. The second one deals with the non-inverting amplifier. And the third one has to do with the inverting amplifier. So let's take a look at all three of these. The first question asks you to prove that the closed loop gain, meaning V out over VI for the op-amp circuit, equals 1. Okay, now if we take a look at the properties of a ideal op-amp, well, the ideal op-amp actually has infinite gain. Okay, actually has infinite gain. Now that gain is typically larger than 100,000. So here, when you have a non-inverting input and you give a input signal at the non-inverting input, you would expect some sort of output you'd expect V out to have some sort of output, right? Now, the gain of the circuit is 1 because when V out is given back as a negative feedback right here, the difference between the two is equal to 0, meaning the total input voltage V input goes to 0. The difference between the two inputs is 0. And the op amp actually amplifies that difference. Okay, the op amp actually amplifies that difference. Now, there are multiple ways to actually express how and why this circuit gain is actually equal to 1. Okay, one of the ways is basically to state that since the input voltage is equal to 0 and the inverting input terminal is V1, and we say there's a short between the input and the output, so we can automatically state that VO should be equal to V1. Now, in reality, what happens is, of course, that if this was an open loop amplifier, the open loop gain, which is greater than 100,000, when you first flip the switch on and the circuit's not at steady state yet, there is a slight difference in the input. And because there's a slight difference, V out is going to amplify it and going to give you an output that's very, very close to V1. When you give this as negative feedback, the difference between the two is going to be very, very close to 0. And again, that loop continues. And thus, the output always follows the input. And hence, the circuit is known as a voltage follower. Output always follows the input voltage. And this is only true for the inverting and the non-inverting terminals, right? Meaning the output at the inverting terminal is always going to follow the input at the positive terminal. It does not work the other way around, okay? And so that's an explanation for how the output actually works, and the gain comes out to be 1, all right? And we can also see that mathematically in the next question. So if you look at the next circuit, which is right here, in this circuit, we are asked to again find the closed loop gain VO over VI for the circuit below. Now, the way you would analyze this is by applying simple techniques. You want to obtain an expression for VO over VI. VI is, of course, the inputs going here, which is V1 minus Vx. So I've labeled the voltage at the inverting terminal as Vx. An inverting terminal is connected here at this node right here on the right. So that's Vx. There's a feedback going into the negative terminal from the output via RB and RA. And if I apply circuit analysis techniques, I can apply KCL at this node right here. So you apply KCL at this node. If you apply KCL, let's get rid of this. If you apply KCL, I can get an expression IRB is equal to IX plus IRA. Well, we already know from the properties of an op amp that IX would go to 0. Again, 0 amps entering. Okay, IX goes to 0. So we get IRB is equal to IRA. Describe each one of these currents in terms of the node voltages and Ohm's law. So apply Ohm's law. And describe each voltage, each resistor voltage in terms of the node voltages. So you plug those into this equation and you should obtain, rearrange the terms, and you would obtain VO over VI. Okay. Now, the critical thing to understand is, of course, that you have a virtual short between the two terminals. And if there's a virtual short, that means that Vx is equal to V1. Okay. Vx is equal to V1. And so when you find VO over V1, which is actually VI, So VO or V1, you would get an equation in terms of RB and RA. Okay, and that's your answer. The second part of the question is, can this op amp attenuate a signal, or can this op amp circuit attenuate a signal? Attenuation is of course reduction. So once you have that equation, you'd be able to answer whether this can work as an attenuator or not. Okay, why or why not? Also, to tie it back to question number 1, if you compare this circuit to the voltage follower, you can write RB is equal to 0 ohms and RA as infinity. You plug these values into this equation that you obtain, and you'd be able to see that this equation would come out to be 1 for that voltage follower. Okay, 1 for that voltage follower. So that's the mathematical proof of the earlier circuit in 1. Now, let's look at problem number 3. So, question number 3 asks you to solve for this inverting amplifier. It's asking you to solve for the expression and asking you to sketch V out. So it's asking you to sketch V out. Okay, sketch V out. Now, RA is given as 1 kilo ohm, RB is given as 10 kilo ohms. V1, the input is given as cos of 628 t volts. If you compare this to the standard expression for a time varying sinusoidal waveform, you get V in of t, which is V peak cos omega t plus theta. You can extract information about the peak value, Vp or Vm, right? The peak value or the magnitude, which in the waveform right here, if you remember from EE201, is 1 positive peak or 1 negative peak, right? So it just gives you information about 1 peak. This image right here, illustration, shows you a typical sine wave, right? It shows you a typical sine wave. The expression is for a cosine. If you again remember from cosine waveform is 90 degrees out of phase with the sine wave. So the positive peak occurs right here at time t equal to 0. Okay, I will leave it up to you students to actually fill in the rest of the information for a cosine expression. All right, now going back to this expression right here, we have Vp and Vm. Then you have omega, right? Omega is right here. And that omega is equal to 2 pi f, where f is the frequency, which is the inverse of the time period 1 over t. And the t is basically here, 1 cycle, 1 complete cycle. So there you have it. That's the information that you need for the input. Now you calculate the output voltage. Once you calculate the output voltage along with the gain, you can actually sketch the output waveform. The only thing you have to be careful about is basically the phase, right? The phase. If you look at the circuit diagram, the input is going into the negative terminal. So the input is going into the negative terminal. The output waveform is 180 degrees out of phase of the input. So V out is 180 degrees out of phase with V in. Okay, your V in is right here, the cosine waveform. So whatever output you get has to be exactly opposite of that waveform. And that is the work that you need to show. Okay, for the output waveform, you need to calculate Vp, right? The peak value of the voltage for the output. Omega, of course, remains the same. And then, of course, the phase, right? Phase, of course, is 180 degrees out of phase of the input. Calculate, find out the input phase, and then just add in minus 180. All right, so that's Prelab number 4. reach out to your professors, reach out to me if you have further questions. And good luck with the pre-lab.